I want to briefly review the idea of a magnetic field. In an earlier video, I've talked about the meaning of electric field. Now, if this is an electric field, it means that if there is there's say a charged particle at this point. There's a charged particle at this point. Then the direction of the field, the direction of the field lines, would tell me the direction that a force would act on the charge. Now, but what about for a magnetic field? Is there such a thing as a magnetic charge? Unfortunately, there is not. Things are a little bit more complicated for a magnetic field. If there isn't a magnetic charge like an electric charge, then what is the meaning of the magnetic field? Well, the answer is a little bit complicated, but one way to understand this is that if I imagine that instead of having a single particle of magnetic charge, suppose that I have say a long piece of rod here, a long piece of magnetic rod, okay, with the North Pole here and the South Pole there. So this South Pole will be quite far away, where the magnetic field is quite weak and can be ignored. Now this North Pole here would be in this region of the magnetic field. Then what the magnetic field lines can tell us is the direction of the force that would act on the North Pole of a magnet. So if I have a North Pole here in this magnetic field, then the direction of the force on the North Pole would be given by the direction of the field lines. So it is as if the North Pole of a magnet is, if you like, is a positive electric charge. And in fact, that is one way we can think of it. We can think of the North Pole as a positive charge and the South Pole as a negative charge. That means that, for example, if I turn this magnet around so that the North Pole is here and the South Pole is there instead, then I could think of the South Pole as a negative charge, so that the direction of the force on the South Pole would be in the opposite direction to the field. In the same way that if I have a negative charge in an electric field, the force would point in a direction that is opposite to the field lines. So if I can think of the North Pole as a positive charge and the South Pole as a negative charge, can I just put a North Pole here on its own? Can I just have a North Pole on its own, put it here and let it experience a force, like maybe like this, just a North Pole there? Well, unfortunately, there is no such thing as a single North Pole that is not connected to a South Pole in a piece of magnet. For many years, the idea has been around, in theory, about a North Pole or a South Pole on its own. This is called a monopole, a magnetic monopole, which you can look up if you're interested. Magnetic monopole. And it is an interesting idea because a magnetic monopole, if it exists, would behave like a single positive or negative charge. And then the magnetic field, you can just think of a magnetic field as completely similar to an electric field. But unfortunately, after many years, magnetic monopole has still not been discovered. So today, we have to accept, at least for practical purposes, that the North Pole and the South Pole must always come together on the same piece of magnet. But even so, we can still think of, it is still convenient to think of each pole of the magnet as like a charge, like a magnetic charge. Okay, so that if I have a magnetic field line, the South Pole would follow a direction, would experience a force like a negative charge in an electric field. A North Pole would experience a force like a positive charge in an electric field. In this, so far I've talked about using a long magnetic rod so that we can focus on, say, just one pole and ignore the other pole, which is far from the field. Now, but what if I have a short piece of magnet, like a compass? If I have a compass, okay, let's say I have a little compass needle down here. Let's say that's the North Pole of the compass, and that's the South Pole of the compass. And this compass is inside a little case, a little circular box where I can look in to see the needle. So that's a compass. What happens when I put a small piece of magnet like this in a magnetic field? If I have a small piece of magnet, each pole would experience a force in the same way that I described just now. So the North Pole would be like a positive charge, and a positive electric charge, or magnetic charge, if you like, and it would experience a force which is in the same direction as the field line. So in this case, you could imagine a force on the North Pole acting in this direction. As the South Pole would be like a negative charge, it would experience a force that is in the opposite direction to the field lines. In this case, it would go there. So clearly, if I have a force pulling this way on one end and the opposite way in the other end, at the other end of the magnet would rotate. The magnet would rotate. Okay, so what would it end up looking? It would end up getting rotated so that it is now pointing in this direction. The North Pole here and the South Pole there. Okay, that's the pivot, and that's my casing is still here. A circular case. It would end up looking like this because, as we've seen from the forces, the force on the North Pole would pull it this way in the direction of the magnetic field. The force on the South Pole will push it in the opposite direction to the magnetic field. So once it reached this direction, it will stop. Right, the force will be in opposite directions along the same line. So it will stop rotating, and that is why if I have a compass, if I put a compass in a magnetic field, the compass will point along the same direction of the magnetic field. And that's also why that there is this idea of there is this use of a plotting compass. If you've heard this term, a plotting compass, before, you know, a compass, we use a compass to tell us the north and south directions. But a plotting compass has another use. It is used in a magnetic field to plot the field lines. And what this means is that, let's say I want to plot some field lines. I can put a compass here. Then I know that the field line must be in this direction. So when the compass is here, I know that I can roughly draw a line from the South Pole to the North Pole to represent this part of the field line. And what I can do is I can then move this compass here. Right, I can move this compass over here. When the compass is over here, the field line would have changed direction a bit. So maybe when I'm here, the needle would be a bit tilted in a slightly different direction from there. So this means that I would know that when it comes here, the field line would have bends. Right, the field line would have bends. So in this way, I can keep drawing short pieces of the field line by moving the compass around. So that's why we call it plotting compass.